So my name is Dave Stanke, and I'm a developer advocate at Google, and I am here to talk to you about continuous integration testing. This talk's not about Istio, but it is kind of Kubernetes-ish, and it's about testing, and hopefully you'll find it interesting. One, integration testing is hard, but we can do it anyway, and we should do it anyway, or at least we should consider doing it. And I'm going to show you a few ways that it can be done. This is within a Kubernetes microservices context, but the techniques should apply to anything that is a multi-component application. So we talk about this in the context of shifting left. Well, what does shifting left mean? It means incorporating critical processes early in the SDLC. So a typical flow, code, test, deploy, operate, cycle back, and we model this from left to right. Shifting left means we do some of the important stuff more lefty. In a traditional flow, a waterfall type flow, often you would have a lot of separate teams working on code. They would all come together at the very end, and then at the very end you'd do some testing and you say, wait, this thing's bad, send it back for 6 weeks before it comes out. Now we've learned better, and we've learned that there's important benefits to be had by shifting left. So what do we shift left on? Well, first of all, we can shift left on merging our code. And this is the original meaning of continuous integration. Instead of having multiple teams all coding independently, crashing them all together at once and having these merge conflicts. Does anyone remember the capital M merge, the merge? Everyone get ready for the merge. Everyone cancel all your plans. We're doing the merge. We don't do that anymore, right? We do continuous integration. And the benefits we get are that our merges are so much faster. We can fix problems while they're still present in our mind. You can also shift left on security. And this is a hot topic these days. It's not what today's talk is about, but you can find a lot of great resources online. Shifting left on security means incorporating security practices early so that you don't have nasty surprises and you don't have long pre-launch times when you do some security review and you're excited to get your stuff out the door. And you can shift left on testing. And that's what we're going to be talking about today, incorporating more testing earlier in your SDLC. So why do we want to shift left our testing? Well, you're probably familiar with some of the research done by NIST and IBM and certain other organizations that say a bug that's found in production is exponentially more expensive to fix than one that's been found in the coding process. Some studies say it's 6x, some say 30x, I've heard 100x. I don't know the exact number, but I know that it's significant. And why is that? Well, I would say one reason is that if you catch your bugs early, preferably before they even go to prod, they haven't had a chance to cause any downstream effects, like data corruption or angry customers. The other reason is about developer flow. If you're still in the zone and you remember all of that code in your head, you can fix it a lot faster than when it comes back at you 2 months later, or maybe you're not even at the company anymore. Science has proven this. These are the results of some study by Nicole Forsgren, Jez Humble, and the DevOps Research Assessment, DORA, who puts out this State of DevOps report every year, and a great book called Accelerate, if anyone hasn't read that. And what they have shown using science is that continuous testing predicts continuous delivery, which predicts things we care about. Software delivery performance, meaning how fast we get our code out to our users, and availability, meaning the uptime of our servers. So basically, testing early and often leads to positive business outcomes. So when we talk about testing, we talk about the test pyramid, right? Who's familiar with the test pyramid? Does yours look like this? This is an idealized test pyramid. At the bottom, we have a whole bunch of unit tests. And ideally, all of our code is covered by unit tests. Every code path has been exercised. Small, they run fast. They typically run within the context of the application and can typically be repeated and rerun on the developer machine all the way up. Then we have a smaller number of integration tests where we test the components together to make sure that the behavior of their interactions is correct. And then we have a smaller number of kind of icing on the cake of these end-to-end tests. This might be something like a Selenium or other kind of UI test that actually steps through the application, makes sure that everything is working. And the numbers of things here is not a coincidence. This is considered to be an idealized way of how we want to do this. But let me tell you what my test pyramids tend to look like. We've got a few unit tests, and maybe we add a few more, but maybe we don't quite have the code coverage we want. We have 0 integration tests because they're hard. And we have one big, messy end-to-end test that's super fragile, and it breaks all the time, and frankly, we probably just ignore it, and it takes way too long to run. So today, we're going to talk about integration testing and how we can get over the fact that it's hard. End-to-end testing, where we layer that on top of integration testing, has a lot of the same problems and same solutions. So we're not going to talk about that today, but generally the same things that I'm going to talk about can be extended to ETE testing. So why is integration testing hard? Well, one thing, production runtimes and developer machines are not the same machines. It is literally impossible to run a multi-node Kubernetes cluster on a single developer machine. Cost, nobody likes spending a lot. And if you're spending more on your integration testing infrastructure than you're spending on your production server, you might have a CIO come in to knock on your door. Speed, and this is one of the bigger ones, that integration tests often take more time, and they involve setup and teardown, and that's going to slow down the developers. And no one wants to slow down the developers. They're expensive. And finally, side effects. So this can be a couple things. One can be the integration test infrastructure that you create might stick around, and you might pay for it longer than you really want to. And another thing is that it can be tempting to test against shared infrastructure, including production infrastructure. So something that I've been guilty of is saying, well, it's just a read-only call to the API. I'm going to use the prod API. I've also been guilty of having that totally break prod, because it's possible for that test to spit out so much load that I'm overwhelming the production API, or even potentially to spit out a bad, malformed API call that somehow crashes the server. So we really would like to avoid having tests that create side effects. Integration testing is hard, and microservices make it harder. The whole point of microservice is isolation. Each team can work independently, can ship their code independently, and each of the application pieces is independent and doesn't care about what else is going on, right? So why bother? Well, one reason is that API contracts and semantic versioning are not enough. With semantic versioning, we're going to make a promise to other components of the application. I will receive these inputs. I will output those inputs. I won't change them, I promise. I promise I won't change anything unless I increment a major version number. But you know what? It's not true. In practice, anytime you create a behavior, someone's going to rely on it, and when you change it, you're going to break someone. Another reason is this emergent properties of composed systems. Even if all of your APIs are behaving exactly like they should between components, things happen. Weird things happen when they work together. Timeouts get amplified. All sorts of other problems can happen that you just can't anticipate. And finally, I think this is the most important one. Your users are experiencing an application. When your user comes to your website or your application, they're not experiencing a bucket of individual services. They experience a singular experience that takes them from point A to point B. And if you tell them, no, it's fine, 9 out of 10 of my services are working, what are they going to say? Well, your application is 100% not working. So maybe we shouldn't bother, because integration testing is hard. And these days, what you'll hear is a lot of people talking about testing in prod. So this is a movement that advocates that we should treat our production systems as uncertain, and that we should do our quality testing in production systems. And then if there are problems, we should very quickly roll back. So should we throw our stuff onto prod and then figure out if it works? Yes. Testing in prod is good. And the reason is there is no prod but prod. You really can't anticipate whatever's happening until it gets to prod. Things will always break. And your production deployments are uncertain. You should treat them that way. And we should plan for failures, and we should even potentially proactively trigger failures. And that's where chaos engineering comes into play. But let's be clear about what testing in prod means. Testing in prod means having hypotheses, having observability to understand the properties of the system, and then measuring and monitoring afterwards to find out what happens, and being proactive about fixing, and having our postmortems. We should do all of those things. Even given all of that, it doesn't mean that we are necessarily not doing pre-prod testing. The trick is it's all about risk. It depends on what you're trying to do and what your risk tolerance is. So the idea of testing in prod is there will be some errors. Let's learn from them, let's accept them, let's embrace them, frankly. But how many errors are okay, and which errors are okay? That depends on you. If you're running a site that is about memes, then you have a strong impetus to keep up with the culture and get the latest memes on there. You want to deploy all the time. And if there's an error when someone tries to get that meme, what are they going to do? They're going to click refresh, and it's fine. If you're running an e-commerce site and someone gets an error and they click refresh, did their card get recharged? Did we lose out on the last limited edition item? Not quite as good. Maybe our risk tolerance is a little lower. What if we're running the back end of a hospital system? I'm not sure that we can be quite so cavalier about having errors and not knowing when those errors are going to happen. Or what I like to think about is, if I'm going to say I tolerate this many errors per day, what happens if one of those errors goes to my boss? I need to have that conversation with my boss, and I need to evaluate the risk myself to decide how much of this I can tolerate and what I'm going to do when it does happen. So there's still a place for integration testing, and we can still do it. It's hard, but we can do it. What we need to do is make that informed risk analysis. Look at how much can we tolerate having problems in prod, and then what can we do about it? And then continuously optimize our integration testing frameworks to make sure that we're getting the right balance and the right level of assurance for our application. So what are we optimizing for? All of these things: fidelity, isolation, scalability, speed, ephemerality, and cost. And we'll go into a little bit on these particulars. So fidelity. We want our integration testing environment to look as much like the production environment as possible. And we're always, with integration testing, we always need a place to put our components and then observe their behavior together. There's only one prod, and that's where we get into that testing in prod is great. But when we want to simulate that, we want to make something that's smaller than prod, probably, or lighter weight, but has as much of the behavior as we can. Next, isolation. We want our tests to not break each other, and we want our tests to not break systems outside of the testing. Scalability. And this is a hard one. It's very common, of course, to have a staging cluster or a staging server. I know I've often been in that case shouting across the room to my colleague, like, hey, can you stop using staging? I'm going to use it. OK, I'll be done in half an hour, right? We would prefer to be able to have every test have its own test environment. And we can use the cloud to spin this up in parallel and make that choice based on cost as opposed to making it based on we simply cannot scale it out. Relatedly is speed. So we want every test to be able to run at the same time so we don't keep our devs waiting. We also want them to run fast so we don't keep our devs waiting. Ephemerality. Now this one's a little trickier. When we create that test infrastructure, preferably it only lasts as long as we need it. But how long do we need it? When the test runs well and we get information back, then we're done. If it's a success, we got our information right away. The test passed, and we should tear down that infrastructure. But if it's a failure, we might want to go in and tinker with that server, to run some scripts on it, look at log files, whatever it is. So the right ephemerality is a little bit of a gray area. It sticks around as long as it's valuable to you, but no longer. And finally, cost, because, of course, cost. All right, let's take a look at an example of how we can do integration testing against an application. So here is a simple application, a microservice application with two services, a web front end and a MySQL backend. And this is only two, not a huge elaborate microservices application, but we all know that there are only three numbers, 0, 1, and infinity. So this has infinite microservices. Each of the services is independently packaged and can have independent component tests, but we want to run them together to find out how they're doing. This runs in Kubernetes, and as I mentioned before, my developers don't all have a 30-node Kubernetes cluster sitting under their desk. That would make their legs really hot, probably. So we're going to look at some ways that we could test this without providing that infinite clone of prod. Here's the flow that we're going to do for our tests. First, we're going to build a couple containers, provision the infrastructure. And so this is usually an integration test called a system under test. So that's the place where we produce an example of all of our components running together, and then we're going to kind of poke at it and see, is it exhibiting the behavior we want? And in this case, it's a very simple one. It just runs a shell script that curls the endpoint and says, is it, oh, I should have mentioned, if you want to play along at home, please clone the repo. You can find the URL down at the bottom right there. I'll also post it on Twitter after this. So it's got that curl script, and then just looks for a keyword. This, of course, can get much more elaborate. And then at the end, if it passed, we want to deprovision it. If it didn't pass, maybe we want to deprovision it. So here's a few different ways that we can do this. One, Docker Compose. Docker Compose is a system that allows you to spin up multiple containers and provide networking between them so they can operate together. In that way, it has some overlap with a Kubernetes or a Docker Swarm. But it's different from either of those. It's simpler and lightweight. And in the example, we use Cloud Build. Cloud Build is Google's hosted CI/CD system. It's fully managed and has a generous free tier. The way it operates is it models your builds as a series of containerized steps, all taking place in a shared VM. At the end of the build, that VM is destroyed, and the next build starts a brand new fresh VM, and the isolation is complete on that VM. Only that one workload runs within that one. So the process is we're going to start by cloning from Git. We're going to build our containers, run unit tests there, and then with Docker Compose, we're going to spin up sister containers to those containerized execution environments, web and DB, run our shell script, and at the end, it all disappears because the VM disappeared. So this is great because it's fast. There's zero chance of orphaned resources. The entire thing disappears at the end. The downside of this approach is Docker Compose is not Kubernetes. So to do something like this, you need to maintain two sets of configs. You have a Docker Compose config, and you have a Kubernetes config. Of course, that can have drift. On failure, you can't debug. And I've spent a lot of time with this particular example, emitting logs and trying to capture them into buckets. It's hard. It's really hard to figure out what happened after the fact. And finally, a particular issue that is relevant to all microservices is startup order issues of trying to get the web to start up after the DB comes up, and when you have more and more, you get more and more complications of the application isn't going to work until all of the pieces have come up. Of course, we have some of the same stuff with Kubernetes, but there's a whole way of dealing with that. With Docker Compose, it's a whole different way of dealing with that. So this one wins for being fast and lightweight, loses a little on maintainability. So if we're deploying to Kubernetes, why not test in Kubernetes, right? So here's an example that uses a standing staging cluster, where we have a staging cluster. In this case, we're going to use Google Kubernetes Engine, but this would work with any Kubernetes provider, including your own. Do our same build, our unit test, and then we're going to use kubectl to create a new namespace for this test. Every single test gets its own namespace. So I could have 100 developers. They could each even be running multiple tests. And they're all isolated from each other using Kubernetes namespace isolation. So each one has its own copy of the web and the database containers. Then we're going to run our test against them. If it passes, kubectl is going to go in and destroy the namespace. One nice thing about that is if you delete the namespace, it deletes everything in it just like that. So it's really quick to clean up. The benefits of this one are you've got that high fidelity because you're running on Kubernetes, just like in prod. It's fast because the clusters already exist and you're just doing a quick kubectl apply. The downside are, one, you've got the isolation isn't completely perfect, and here's why. Namespaces are pretty good. And with a namespace, you can say the entire world for these containers is this namespace, except some things in Kubernetes aren't scoped to namespaces. One example is custom resource definitions. So if you want to test different versions of CRDs, you're going to need a separate cluster for each one. And of course, if you wanted to test your application running in different versions of Kubernetes or different flags on the cluster, you can't do that when everything's running in the same cluster. On failure, if you leave that namespace there, and it turns out you don't need it, it's going to hang around, and that could be expensive. But an orphan namespace in Kubernetes that's just sitting there doesn't really cost that much. All right, so for this next technique, we're going to use a self-destructing VM. A what? A self-destructing VM. So this is, as part of this test, we're spinning up a VM. And that gives us the risk of orphaned resources, right? And VMs cost money even if no one's using them. It costs more to maintain a VM sitting around than just a namespace that's doing nothing in Kubernetes. So we're going to program these compute engine instances to delete themselves after a set period of time. So to do this, we instantiate it with a startup script that sets a timer on the instance. And there's metadata on the instance that tells it how long to live for. When that allotted time has passed, that instance reaches out to the API and says, API, delete the instance with name XYZ. That happens to be my name. So the API reaches back, and I'm gone. If you're interested in checking out this technique, you can find an article there with samples at that bit.ly link. So we've got a self-destructing VM ready to go. Now, in this case, we're going to run our Git, run our build, and we're going to use Terraform to provision that VM. And that VM is running something called microservice, which is a single node Kubernetes instance. It's actually Kubernetes compliant, so it keeps pace with the latest version of Kubernetes. There are a couple other versions of this. There's Minikube, there's K3s, and they're all effectively the same idea, which is it's a smaller, lighter weight Kubernetes that you wouldn't want to run production traffic on, but it's good for testing or for dev. So we're going to create that VM, drop our stuff onto it. In this case, we have an entire Kubernetes cluster to play with, even though it's only a single node cluster, run our test, which again could include cluster-wide things. And then at the end, we'll use Terraform to deprovision it when the tests pass. If the tests don't pass, it's going to hang around so that we can SSH in and poke around, see what happened. But if we forget about it, that self-destruct timer will kick in after a certain amount of time, whatever's appropriate for your developers. I think this one is set for default 48 hours, but you can easily adjust that, keep it around for a week, keep it around for just a couple hours. However responsive your dev team happens to be, and poof. So the pro of this, we've got perfect isolation, right? These VMs are complete little bubbles among their own. And we've got high fidelity. These are Kubernetes compliant Kubernetes servers, so you're testing against Kubernetes. The downside is, one, it's not exactly a Kubernetes cluster. I don't know where that's going to fall down. I don't know where you're going to have differences. I'd love to hear about them if they are, but you never know. And the orphaned resources are expensive, even if they only last a little bit of time. Now, as I've been working on this stuff, I've had people ask me, well, why not just create a whole Kubernetes cluster per test? And my answer was, man, that's super expensive. No way. But in the interest of science, we have that too. So you'll find in the example the ability to provision an entire Kubernetes engine cluster using gcloud, and then deploy, again, just the one little workload into it, run the tests, and then at the end on success, gcloud will tear it down. Believe it's possible to create a self-destructing Kubernetes engine, but I'm not sure. I haven't tested that one yet. But regardless, the good news is obviously a full-on, absolute high-fidelity test. Bad news is it's going to be more expensive, and it does take longer to provision a Kubernetes cluster than it does to provision a single node running a lightweight version of Kubernetes. All right, so putting it all together, we have all the pros and cons of these different approaches. Really, it's all trade-offs. There's no single best answer, and it depends on what you're looking for. I think in a lot of cases, you may want to use different techniques at different times. For your pre-submit tests or pre-merge tests, you may want to use something small like the shared K8s. If you want to get a final last, is it okay? And if you have a low risk tolerance, you may want to go through the expense and time of spinning up an entire cluster for each test to make sure that you're really rock solid. And after that, you should test in prod. There's a lot of opportunity for that too. However, on balance, I do think there is generally a best solution, and that's this one, the shared staging cluster, where all of your developers share one, or they could share more than one, but if you've got auto-scaling involved, there's no real reason to have a bunch of these. And all of their workloads are living side by side with the isolation of namespaces, if that's sufficient for your application. Normally, I would be loath to tell people that they should have all of their engineers sharing a single piece of testing resource, but the isolation really is pretty darn good. And the cost savings from that, that bin packing of everyone using the same one is really good. It's also fast. The thing's already sitting there waiting to be provisioned and deprovisioned. But Dave, or Dan, what about lots of services? What if I've got dozens of microservices? Well, that gets hard. And in that case, it comes to how do we make trade-offs? We have to make compromises between launching all of the services up for every single test versus maybe having standing resources, preferably not prod, but standing examples of staging services. We can use mocks or stubs to simulate some of the things. It may be valuable to have a simulation database, let's say, that just returns the same query every time, but all of your other things are live and you're getting the latest versions. Also, you can use semantic versioning. That's also known as hope as a strategy. Dave, what about databases or other things that are outside of my Kubernetes cluster, assuming I'm not running a stateful Kubernetes load? This is, you can absolutely run these things as ephemeral. You can run a database inside Kubernetes in the test. So that's what the example app is like. You can certainly spin up a cloud service per test. Expensive and heavy, but you can do it and isolate it for each test. Or you can call out to external stateful things. You might maintain a staging database, but your application you provision every single time. But Dave, what about test data? That's hard. Ideally, your tests are running against a database or a data store that is as complicated and as large as the one you have in prod. Complicated is important for the behavior, large is important for the performance. That means taking your production database and cloning it into your staging environment. But that's problematic. It's too big, and you've got probably customer data that needs to be scrubbed. I don't know of easy solutions here. One is to maintain a full test data as part of your test infrastructure so that whenever you make a change to your application, you're also changing the queries that update your test data. That's not bad. It would be awesome to have scripts. I've done this, to have scripts that take prod data, scrub it, sanitize it, maybe even subsample it. That's pretty hard. I have heard that there are people working on problems like this, and I think it's a really interesting space. So to wrap up, yes, we can still do integration testing. And depending on our risk tolerance, depending on our customer needs, we probably should still do integration testing. It's hard, but you can do it. The important thing is to analyze your risk, ask what happens if these things don't work correctly, ask how fast can we make it, how cost-effective can we make it, and how close can we match prod using the tools that are available to us. Find your own sweet spot, and when you do, please tweet at me. Thank you. And so I have questions, time for questions if you do. Yes. All right, so the question is, what percentage of tests should we run in prod versus before prod? And I think this is an evolving space, so I'll just give you an opinion, which is I actually tend to think that we shouldn't necessarily be running tests per se in prod. Testing in prod, what that means is you've got users running tests for you. The users are going to run through sequences of clicks, things you can't imagine. You've got more load probably than you have on staging. I tend to actually think that load testing is something that's best left for prod. So instead of running a test suite, you take your application, stick it up there, and it's about observability, and it's about gradual rollout. So roll out your newest version to 1% of your traffic, have close monitoring and observability to find out what happens, and let the users do what they're going to do. If it's bad, roll it back real quick.
Okay, so not really running the actual test suite in prod. That's not really
right, because the test suite is, no matter how good we make it, it's going to be our guess of how people are going to use the application. In prod, by the time it gets to prod, we've got the benefit of we don't have to guess. Let them tell us how they're going to use it. And that comes back to that risk trade-off of the more you run pre-prod tests with your best guess, you're limiting risk. But you can't limit it all the way. And there becomes a point where it's like, you know what? Rather than trying to exhaust all the possibilities, and I'm still not going to get it right, at some point, I kind of put it out there with the right guardrails in place. Yes? The question is, do you see people dealing with a test data problem by using a container with the test data loaded into it? And the answer is yes. And that sample application actually has that. Has a MySQL application that loads in a test database. That's stored in source, testdata.sql, and then you can update that as you go. Again, the problem is going to be like speed. It's like, if your prod database is 4 terabytes, that's not even big anymore, is it? I'm old. Then you're not going to load that into a container and wait for it. Databases are a hard problem. Other questions? Anyone? Yes. Great question. The question is, are there solutions that would let you record what the real users are doing and play them back as part of your test suite before your next version goes to prod? The answer is there are solutions. I don't know details, but it makes a ton of sense. Don't guess what the users are going to do. Subsample what they're going to do and play it directly on your code. Absolutely. All right. Thank you, everyone, so much. It's been a pleasure, and I look forward to sharing the rest of the conference with you.